Hi everyone, welcome to the distinguished lectures of the Qiskit Global Summer School. My name is Junye. I'm the global lead for Coding Challenges and one of the main organizers of this event. So today we are very honored to have Professor David DiVincenzo to give us a distinguished lectures, to give us like the historical perspective of how in the early days that we do different kind of physical realization of qubits and how he came out with the DiVincenzo criteria, which is very famous for. And David DiVincenzo is our professor of theoretical physics at RWTH Aachen, and also director of the Institute for Theoretical Nanoelectronics at a word that I don't know how to say in the German, in the Institute of Zurich. And before that, he was in IBM research as a research staff scientist, where many of the work early days that he had done was in it here, including the DiVincenzo criteria and also the spin qubits proposal. And before we get started, I also want to share some personal anecdotes. As I posted on LinkedIn, if you'll see, it's about 10 years ago, I joined a summer school in Singapore, Port Harborsea. You can see Professor here in the middle. And I was here. And so I feel like it's a full circle. And that summer school was very pivotal for my own career. And it convinced me to pursue a career in quantum computing. And here I am after 10 years and in IBM Quantum for 5 years and hosting another summer school. And hopefully we can inspire a new generation of people to pursue this career. So without further ado, I give the floor to Professor DiVincenzo, please.
Okay, thank you, Junji. Thank you for your kind words. So, as you said, I've been asked to play the role of historian here and tell a little bit of the story of how we all got to where we are today. But even looking, quite far back into the 1990s, and I'll even reach even farther back in time than that. But I'll be concentrating on things that we were learning in the 1990s and also the 2000s that were very pivotal to getting us to, the threshold of real quantum computing. So here's a little outline. I'll begin with very early thoughts about computers because I've somehow been managing throughout my entire life to intersect with computers. I'll talk for a moment about the ENIAC and what it meant to me. The ENIAC was the first digital computer 80 years ago. Then I'll move on to things concerning the quantum world and quantum computers and the qubits. I'll talk about my early time at IBM and how I was influenced by Landauer and Bennett and others, but really what were the ideas that were going around at that time. It was really Bennett who prompted the creation of the word qubit, although he's not credited with it directly. But we were very concerned at that time with what could be a real qubit, and I'll tell you what the first tries were, and some of them were not promising and remained unpromising, and some of them have ended up being very promising, but took many twists and turns before they really got going. And for the current millennium, I'll be telling in a little bit more detail about spin qubits and also about superconducting qubits, mainly concentrating perhaps on the superconducting qubits you never heard of, because they're, the sort of pre-designs, the ones that almost made it, the ones that were very crucial to getting us to the real working designs that we have today. And I'll tell you, even in the early 2000s, we were already beginning to think about architectures, and I'll give you a few of those things. They were just the seeds of ideas that have become, I'll say, very, very big and very prominent in the current world. So, yes, my early life with computers. So here's just a picture of some things. Of course, I'm not quite this old, but to me, the subject both of computing and also of modern physics begins with the Crookes tube on the right, because the Crookes tube is the instrument with which the electron was first discovered, but the discovery of the electron came along with the understanding that it was possible to control the flow of electrons through vacuums. And after many decades and twists and turns, even longer than the timeline of our quantum computers, we came to these devices that I show here And I'm sure you've seen these pictures, racks and racks of vacuum tubes and people constantly maintaining them. But this was the computer, the ENIAC computer that was built uh, now 80 years ago and functioned for a few years before it was superseded by another computer. It itself superseded the computers of the time, which I show in the bottom left. At that time, what computer meant was um, people who were very good with figures writing on pieces of paper. So we, of course, transitioned out of that era, but we've had long time and many stages of computing machines. So the ENIAC was superseded by the EDVAC, which was conceived of by von Neumann. And his concept was documented in this work, but it was very much inspired by ENIAC. Now, ENIAC was a product of the University of Pennsylvania, and more specifically of the Moore School of Electrical Engineering of the University of Pennsylvania. The reason why I mention that is that this was and is still the Moore School of Electrical Engineering, right in the middle of Philadelphia, and it's the place where I studied. So I came to start taking lectures in 1976 in the lecture halls that are through the windows here. In the windows of the ground floor were the experimental halls of the ENIAC. So the photos that you see of all the people, putting vacuum tubes into racks, they were in that big room, which when I studied 30 years later was the room where we did our lab work. So we had our, exercise labs, learn how a transistor works in those rooms. All remnants of that original computer had long since passed. And I even started my research career in this building on the other side, up in the upper reaches in 1978. I started doing research, and that was actually on materials, which were graphite materials. And at that time, we didn't think that had much to do with computing, but nowadays we do think that those materials have something to do with computing. Now, after that, after a few years, or actually starting in 1980, I was already some of the time at IBM and was regularly at IBM Watson Research in the 1980s. If I had been really thinking about it, I would have known that there was already something new coming in computing, because already in 1982, Feynman had articulated the idea that there should be a new kind of computer, the quantum computer. This was definitely well known to some of my IBM colleagues, but not me. I was still working on graphite and things like that. But I give a lot of credit to my IBM colleague, Rolf Landauer, who already long ago, from the time I was born, was thinking about the connections between fundamental physics and new forms of computing. I have on this slide a few other people whom I won't really talk about, but which this illustrates that there were ideas about new kinds of computing and new kinds of quantum effects, quantum communications by these two gentlemen, Holevo and Manin. And if I had been able to read Russian in 1980, I would have read, and this is the text of Manin, who says in not so many words, the basic idea of a quantum computer, and actually predating Feynman's initial writings about that. So this concept was in the air, but it took a long time. In 1980, there was no significant work towards a quantum computer. I would say, though, or to build up to that, there were many things that were building up towards a new kind of information processing technology. My personal exposure to a first thing that you would call a qubit was in the early 90s, when I was working with an IBM experimentalist, David DiVincenzo, and he was actually working with biological nanoparticles which were magnetic. And he was looking in his experiments for quantum effects, for things we would call today the quantum energy states, the 0 and 1, if these were qubits. Now, these magnetic proteins did not make very good qubits, and our theory at that time showed that it didn't. But perhaps more influential for me towards stepping towards the present day quantum computers was another IBMer, Charles Bennett. And he had been a protege of Landauer, but he was definitely bringing these ideas much farther forward. And with his other collaborator, Wiesner, pictured here, but Bennett's the one on the left, he pioneered, first of all, the notion of quantum key distribution. But during my time at IBM, he was working quite hard on coding and communications and the actual experimental realization of quantum key distribution. So I don't know how many in the audience know anything about the IBM Watson Research Center. It's a one big giant building. And so the work of Absalom was in aisle 1 of the building, really, I think, right at the epicenter of current quantum computing work. But the first qubits at IBM were created as a desktop model of quantum cryptography in aisle 27 of the big building. And it was that work that I witnessed and which persuaded me that it was a great new field to get into and to think about. And in 1993, Bennett introduced the idea of quantum teleportation. And that, I'd say, really was what got me hooked and got me feeling that this would be a new trend for computing and for information processing. Now, that turned out to be a good call because in early 1994, we had very big news from Bell Labs, and this is just from my own archive of emails. In 1994, we did regularly communicate back and forth with emails, and these are emails between me, DiVincenzo, and Charles Bennett, Bennett C. And it was about, Peter Shor's work, and we had been receiving, regular updates of his latest preprint on the subject. We invited him to come to IBM, and he came in June of 1994. We were worried that our auditorium would be, or our seminar room would be too small for the overflow. And so we got a very firsthand account of his work. And this is the first slide that he showed in his seminar at IBM in June of 1994. So we were very much on top of this, and it made it very clear that this was a subject that needed very strong attention, because even with the discovery of this revolutionary algorithm, there were no very well-formed ideas of what it would mean to build the machine that would accomplish this, would really make the quantum computer. So what was going on? Well, we did indeed launch immediately into the question of what could we use to make a qubit. It was already clear that it's not just that operating a transistor circuit in some different way, at lower voltages or something like that would suffice, that it was clear that it needed some radically different physical platform in order to accomplish what was needed for qubits to function. So a first effort, which took us some distance and was several years of research at IBM and other labs around the world, was to use nuclear spins for quantum computers. So in this slide, I feature, after a few years of work, the experimentalists came upon this molecule, this metallo-organic molecule, carefully chosen to have 7 nuclei along this backbone, each of which was a 2-level nuclear spin system, a so-called spin 1/2 system, consisting chemically of fluorines and carbons. And if you know your history, you know that this computer, so to speak, achieved the feat of factoring the number 15 around the year 2000. Now, in the introduction, it was said that I was going to tell you about the criteria for a quantum computer, and they were, I was well underway in formulating it at this time, but I can say that a large motivation of me writing down these 5 criteria was to explain why the NMR quantum computer was not going to work, that it was actually, it had some of the elements of a quantum computer, and it allowed us to demonstrate some aspects of quantum computation, and it taught us somewhat about how we would what kind of instruments we would need and what kind of controls we would need to run a quantum computer. But it was clear that it was a dead end, that it was not a scalable concept. It also had the feature that it was not possible to initialize the qubits. It was not possible to set them all in the zero state at the beginning of computation. So by several very elementary criteria, this machine could not function as a quantum computer. And indeed, history has shown that this was not the golden path to quantum computation. So now I thought I had ideas for what would be a better way, and it was based on other work that was going on in those times. Now I'm 1996, but I had already known about this work for a few years. So these are experiments. They were done by Carol Livermore, the photo here on the right. He was a young worker at Harvard University, and they were working on so-called Coulomb blockades. So they were working on electrons that could hop in and out of these two quantum dots labeled N1 and N2. And what would really catch your eye in 1996 was that they had a picture which on the face of it would say that, yes, they could actually put one electron in the left dot and one electron in the right dot. That would be 1, 1. Now, in fact, there was a big offset in these experiments, so it was more like 101 rather than 1. And I'd say the experimentalists were not so clear at that moment about whether they could make that 1 actually 1 rather than just varying the number 1 at a time from 101 to 102 to 103. But it was enough for us to start thinking about that and to come up with ideas for how to build, much more concretely quantum computers using this platform. But I'm already a little ahead of the story in the sense that I wanted to back up and tell you about, you might say some false starts that were a little bit along these lines. So my very first publication on quantum computing, which was this one, established two things, had two main thrusts. One was to establish the basic principle that two qubit interactions would be enough to encode a quantum algorithm. This sounds, surprising that this even was ever a question, but the literature as it existed in 1994 would have led you to believe that you needed three-body interactions, which are possible in quantum physics, but much more exotic. So in this paper, I showed that, with the suitable decomposition of operations, you could decompose them all the way down to 1 and 2 qubit gates. And that became very much the dogma afterwards. We say 1 qubit gates and C-naughts are enough to do quantum computing. The other part of this paper was that I already took a stab at what quantum systems would be able to encode qubits. And if you look at this list, I think it has some interesting, features. It called a few of these right in the sense that electrons in gallium arsenide became a very viable qubit, and that was already based on things that I knew about in these Harvard experiments. Trapped ions definitely became a trend. Nuclear spins became, as I said, a bit of a false trend. The Mös-Bauer effect, never became, has not up to this time formed the basis of any qubit. What's also very deficient about this list is something that, if you look back, comes essentially from Feynman's thinking, but which I repeated in this paper, that I said, surely a qubit will involve one or a very small number of elementary particles, atoms or nuclei or electrons. And that was very wrong, as it turned out, but we had to learn that. But it was other workers who came to that realization. Of course, I'll come to that as I go through this survey. Now, I was also very mindful at this stage that one should have not only a qubit, but also sort of a system in mind. And so the left-hand side shows the, quote, system, but let me explain that in two parts. So I said, well, spins would form the basis, the spin up and down would form the basis of quantum computation, but how would you really move them around? And I offered, frankly, rather tongue-in-cheek, the idea that you would move them around as on a kind of the gearbox, and that the spins would be carried around on the tips of the gears of a kind of gearbox arrangement. Now, as I say, this was not in any way a kind of realistic, line of reasoning. I helpfully offered a picture to try to be more concrete, to say, well, maybe it would be actually a proton bonded to the end of a scanning tip. This of course, never came to anything, but in some strange way inspired then the few years of work on nuclear spin quantum computing. Now, indeed, we have not yet returned to this, although I still sometimes talk to my physicist friends who do scanned tip experiments to say, well, couldn't you put some nice things on the ends of your tips and maybe they'll be qubits? And maybe someday, maybe another 30 years will go by and we'll have some information processing based on that. But no, it didn't indeed come to pass. And so in the next few years, we were really trying to work on things that made more contact with real experiments. And so let me run through what then happened with spin qubits, because indeed, the ideas really leapt ahead in the next few years, 1996, 97, 98, and came to points where they were not merely fantasies, but they were really realistic prescriptions for things that could be done in the lab at the 1 and 2 qubit level. So I mentioned first a concept that is due to a worker named Bruce Kane, who, while he was working in Sydney, Australia, came up with the idea that the qubit would be embodied by a single atomic impurity in an otherwise perfect crystal. And he was very concrete about this, that it would be a phosphorus impurity, a donor impurity. And a donor impurity has the feature that it weakly binds an electron. And so a candidate for the qubit is the spin of that electron. And this cartoon shows pictures from Kane's ideas about how you would manipulate that electron by stretching it towards the top surface or pushing it downward, or sort of stretching them towards each other. What is perhaps interesting about this is that it's an early example of a concept that involved silicon germanium multilayers, which was a real thing in experimental work at that time. Has now undergone a big revival, actually a big renaissance currently in qubits embodied by hole carriers in germanium. So rather different sandwiches than what we came up with. This is a paper that I was participating in as a follow-up to Kane's work a few years afterwards. But you see rather specific compositions of silicon and germanium, and these have become actually even more so than before real parts of the quantum computer discussion up to the present. But the other idea that surfaced was to use things that were much closer to the work that was done at Harvard, the Carol Livermore work. I might say Livermore and Westerfeld. Westerfeld was the senior collaborator, but Livermore did the work. So they had these structures where you would define quantum dots by side gates, and we conceived of a whole scheme, which would be not only that these would be the qubits, but how would you initialize them? How would you do 1 qubit gates, 2 qubit gates? Why would they be highly coherent? And how would you read them out? So we gave, tried to run off the whole checklist and show that, this would be a plausible approach to quantum computing. So as you see, this published in 1998. Now, this did, but I'll say very slowly, stimulate new experiments, not merely continuations of the existing experiments on quantum dots, but efforts to achieve a variety of the functionalities that we had in mind here. This is another figure from that paper where what's shown here, the message in this paper, or in this figure, are a few things. That one, you would need rather special setup to do measurement, and that's with the FM ferromagnetic dot and PM the paramagnetic dot, and you'd sometimes use SV a spin valve. So this is a sort of collage of possible approaches to manipulating qubits, but with an emphasis in this figure on how you would ever read them out. And the other aspect is that we showed these rather irregular, sort of kidney bean shaped dots to emphasize that the shape would not really affect how well the qubits would function, because the quantum information is carried by spin, and spin is not affected very much by the shape of the electron orbital that it's associated with. Okay, so we had laid that out there, and after a few years of work, things started to gel a little bit. We were unsatisfied with how many controls we seemed to need. That not even shown here is we needed so-called micromagnets that was essentially captured by the idea of putting in these ferromagnetic dots here and there, and people did end up using so-called micromagnets. We asked the question, could you get away with not ever using micromagnets? And that brought us to a very early kind of coding idea, which said that no, don't use one single spin as a qubit, but use three functioning together in a certain coded fashion to embody qubits. So this is an example of not an error correction coding, but a kind of error avoidance coding, or a coding to simplify the instruction set. And but I won't tell too much of that story, because I wanted to go on to discussing what then really happened in the lab subsequently. I'd say that almost all of the ideas from these early papers eventually were visited in the lab, but sort of frustratingly slowly. That is, you would hope when you write down some neat ideas that people would start working on them, but you meaning an expert, a theorist like myself, always underestimates how complex it is to get things actually going in the lab. But groups started right away, and actually the first success that I mentioned is another group that was working in the Netherlands at Delft University, and they, with a sort of simplified arrangement of quantum dots, is just a single dot, but they demonstrated in this how readout would work, and it immediately came upon an idea that was simpler than any of the ones that we had introduced. You don't need a special dot or a special material. You just need the right kind of reservoir that the electron can hop into or not. And the presence or absence of that hopping reads out the qubit. This is not quite the method that's used currently, but a very closely related method is, but which is indeed based on the right-hand side of this plot, where you have a so-called quantum point contact. And monitoring the current in a quantum point contact is indeed the current day method of reading such qubits. Now, these experiments moved on to 2 qubits. By this time, it had been mastered, as we had hoped, that yes, indeed, you can set these devices so that there is only one electron in the left dot and only one electron in the right dot. This further work at Delft, however, showed how massive and inconvenient the control apparatus would be. You see this teeny tiny pair of dots in panel A, but then you have to zoom back out to B and C to see how massive the control apparatus, which is delivering the AC magnetic field to control the qubits, to rotate the qubits on their Bloch sphere. So, and this became part of a theme of how one would go forward to larger numbers of dots. And that remained a very difficult problem, and to this day remains a problem of high difficulty. It goes beyond the scope of what I'm going to talk about in my lecture, but eventually, or now in present-day models, we've learned to sort of spread out the qubits more and move them around. But I will say one or two things about the very earliest ideas along those lines. But it was not at all clear in these initial experiments how scaling would work. But at least this, and now this is back to a different group at Harvard, showed successful operation on a Bloch sphere with these quantum dots. But unfortunately, with a lot of noise. And what this paper illustrated, and I blow up something that's shown in the left-hand inset, which emphasized what was really problematic about these quantum dots at this time, which had not somehow been a problem with quantum experiments up to this moment. And it was because of the higher precision, the higher demands that we put on the quality of quantum states that this began to be a problem. What I'm illustrating is a pair of quantum dots. Each of them has an electron in it. Very good. These electrons can tunnel couple to each other. Also very good. But unfortunately, in these semiconductors, there's a sea of additional spins, which are the nuclear spins. And unfortunately, every single gallium has a nuclear spin, and every single arsenic has a nuclear spin. So you have tens of thousands of nuclear spins participating also. And it did not finally prove possible to decouple those sufficiently well for this to be a good platform for the spin qubit. And it was slowly recognized that one had to go back to the more classic semiconductors, silicon and germanium, because they had, at least in one of their isotopic forms, no nuclear spin. And that remains the story to this day. But that transition was very slowly happening through the years 2000. And then also very gradually scaling up. This was a 4-dot and therefore potentially 4-qubit device made also at that same time. But frankly, progress remained quite slow. That the fabrication required to make these devices was very demanding. Achieving the cleanliness required was quite demanding. And so progress nevertheless continued, and also there were a few groups that jumped on the idea of using these 3-spin models. But I think at this point in the talk, I'll stop stop the line of spin qubits, and instead talk about superconducting qubits. Now, the very idea that superconductors could form qubits was against the idea of Feynman, and the one which I accepted initially in 1994, which was that you had to find a quantum effect that would operate at the atomic level. So other people were smarter than me and realized that there are nice quantum effects that operate on far larger scales because they are kind of collective phenomena, and superconductivity being the prime example. So first ideas, now this was by no means the first. Actually, in a sense, I jumped into the middle of this story by jumping to work which came out in 2004. But a few points I wanted to make about this, that in the year 2000, our research group at IBM Watson had a transition in the sense that for the first time, experimentalists were encouraged to think about how solid-state devices would function as qubits. The work of NMR, which was also done at IBM, was done in IBM Almaden, actually, at a different laboratory. But one colleague of mine took up that challenge, and that's the first author of this paper, Roger Koch. And so he was, in some sense, the pioneer at IBM that first dared to do experimental work on superconducting qubits. For quite a few years, he was basically alone. He had a few of us as collaborators, but he led the effort, and he conceived of the qubit. And his concept for the qubit is shown here. And if you are familiar with superconducting qubits, you will look at this and you'll say, huh? And you'll say, gee, I never saw that qubit. And you'd be right. This is not at all a current popular qubit. And sad to say, it didn't really function that well. There were noise problems that took years to overcome. And it's not clear that they were ever going to be overcome. But fundamental understanding was increased by looking at these, and contributions to science came about from these experiments. Now, in fact, as we got started on this, I'll say that I was a theory collaborator and was trying to help with modeling of this, and for a few years, Koch, could feel like, well, he was in the race, but unfortunately, we saw while he was still struggling that other groups were very much taking up this same challenge. And so I'd say a really notable milestone in the sequence of superconducting qubits was this work in Paris of this group that had been doing quantum dots for years and years, but also had been doing Josephson junction devices for years and years, and they came up with their own design involving in this case, three Josephson junctions in a form that's more or less like what's called a flux qubit. And if you in your studies maybe you learn a flux qubit at least as one of the earliest designs. There were papers already in the 1990s that said that maybe designs with three Josephson junctions could be put together to craft a qubit. This one is the first one that showed kind of reasonable Rabi oscillations. So, if you ask fidelity, not so good. Measurement fidelity, 10%. Process fidelity, gate fidelity, well, who knows? Because the spam errors were so large. Let me point out a few things about the micrograph. So in the lower right, you see a picture of the qubit. What was considered the working element was labeled box, which is very small, submicron scale. There's a sort of large additional structure, but large you see measured in micrometers. So now from one point of view, yes, this is very large. It has, 1 billion aluminum atoms. So obviously violating Feynman's premise that you needed single atom action to have a qubit. So here were 1 billion atoms working together cooperatively and forming a qubit. So that surprised many of us at that time. But maybe some of you know is that this model was still a dead end. Quantronium is not the way that we make quantum computers today, because even though it was gigantic, it was still too small. So we hadn't accepted fully the message that go big, that good quantum effects and good qubits would emerge by going even bigger. Now that lesson still took more years to learn. Here's this group that I mentioned at Delft also had a branch that was working on superconductivity. This is the last author, Moy, was indeed the one who conceived of the superconducting circuit, the flux qubit, as a qubit. And here was an instance of his devices. And yes, they showed some kind of gate fidelity and measurement fidelity 10% or something like that. So coherence, but again, very small, a couple of microns in scale. The beginnings of the real breakthrough in this came at work exactly at the same time, but at Yale University. And if you look at the illustration on the right, any of you who know, superconducting circuits as they exist today, say, yeah, that looks pretty much like a model I've seen. I see now a resonator and capacitively coupled. Looks like they know their microwave technique. And then there's the qubit, but you'd look at the qubit and said, whoa, but that qubit is really too small. So you see the panel C is the qubit, and it's again 5 micrometers. So now this experiment that completed in, I say here 2004, but I'm a little confused. I thought it's 2005, that it did actually solve the measurement fidelity problem. This turned out to already show that you could measure qubits very, very well, but the coherence time was quite poor. And so indeed the next development at this lab I'd say the real breakthrough at Yale in the next year or two was to realize that, if I make the qubit a millimeter size, 1,000 micrometers, that would actually make a better qubit. And that was the transmon. But it required the exploration of these intermediate models, these not quite working models, on which many, many years were spent, and whole PhD theses were written on these things, and a lot of productive science was learned, but all in preparation for arriving at the model that really worked. And when it really did work in 2007, it became the established method. But again, I was asked to just cover the 1990s, 2000s, so I leave that story more or less untouched by this lecture. But what we always say is the rest is history. So that's where superconducting qubits got to by the mid 2000s. Now, okay, dreams of a quantum computer. Okay, well, there was my gearbox, but let's, not take that so seriously, and nobody did. But in fact, there were efforts already, before 2005 to envision what the quantum computer would finally look like, even before we had perfected any of these qubit types. So there was indeed a paper in the spin qubit literature that even when, at the moment when you could barely see Rabi oscillations, there was already this paper, Jake Taylor and company. The last author is Misha Lukin, actually. But it actually got many things right that spin qubits, if they were going to work, it was going to be necessary not only to have zones where gate operations would take place, but it would be necessary to have ways of moving electrons around. And they introduced the so-called spin shuttle. Now, spin shuttles indeed are considered the way to go now if spin qubits are going to work. And this already, sketched out a particular idea for the use of quantum error correction. There are so-called Stein code blocks in this picture, and if I'm not mistaken, they invoked concatenation, which means they're invoking very antique and outmoded concepts for quantum error correction, but they did invoke them. They knew that they were there, but it was obviously a very immature moment to start coming up with a whole architecture, but it's, important that these were conceptualized already very early on. Now, the other things that I'll point to now are basically pure theory, but which have definitely had very high influence on architectures and really guide architectures up to the present day. So this is neither the first nor the last paper, but this is maybe one of the most important milestone papers of in 2001 on the use of new techniques, or new at that time, for achieving highly reliable, they say, just quantum memories using coding. And this was invoking the kind of error correction codes that Kitaev had already introduced a few years earlier, the so-called toric code. This invoked the so-called surface code. So a patch of qubits conceptually in a square array, and laid out many of the things that would be necessary to make this a very, very reliable quantum memory, made highly reliable by quantum error correction. And now I like to point out that as an abstract thing, it's often said, yes, and this came about because Kitaev had, worked out these parallel or the basic ideas of this in 1997. I like to advertise that actually if you go back, where were the really fundamental ideas? Where did they come from? They can actually be traced back another 40 years earlier. And in the sense that here's a paper from Franz Wegener, who's actually a well-known theorist, spent most of his career in Heidelberg. But he wrote down a paper which was pure math and which just was exploring new kinds of dualities, mathematical dualities in Ising models. But his version of an Ising model is something that had four-body interactions, and which were exactly equivalent to the 4-qubit checks, X checks and Z checks that were popularized by Kitaev and then used in the Dennis et al. Work on using surface code for memory. Now, of course, these, nothing much happened. This did not influence experimental work in 1971, and also this work in 2001 did not immediately influence experiment, except, I would say it immediately got experimentalist thinking. But this paper had real trouble in the sense that if you asked, well, how well could you do universal logic, they had no good answer. And they said, well, maybe there's sort of some kind of way of doing it. Well, you'd have to be able to pick up a square patch and plop it on top of another patch, very unrealistic, or was considered very unrealistic. And if you did that, yes, it could work if the error rates were 10 to the minus 5. So that was also put it in the realm of very unrealistic, that even very, very optimistic people thought that error rates of 10 to the minus 5 per gate operation was not anything we were going to get to. And that remains indeed true to the present day. Now, what required this to go further, now I'm right at the sort of edge of my period of time, 2005, a paper came out that also looked, how shall we say, useless. That is, it looked like sort of mathematical doodling and some kind of topology and interlinked toruses and things like that. But actually, it was realized that somehow very deeply encoded in this work of Rausendorf was a new concept for how to use these surface codes, and which became good news, very big news, in the coming months, literally, that, and this was my take on it. I just took this slide directly from what I said about this in 2006, because I wanted to retain the sort of surprise factor. Because I said how their topology mapped onto things you would actually do on a qubit lattice. And then in bold, I said, wow. And they say that means that the threshold for successful operation of this as a fault-tolerant, error-corrected computer would be near 1%. So, at 2 or 2.5 orders of magnitude better than any previous estimate for how accessible fault-tolerant operation would be. And that became, a real target, and that remains the story pretty much to this day, that error rates in this range, or somewhat better error rates, but not enormously better error rates, are the ones that are concretely targeted for actual error-corrected operation. So this work of now nearly 20 years ago was the one that established that as a theoretical possibility. And then there were many works that filled in the details of this. But what was really of interest to us, and now indeed to tell this architecture story, I tell a little bit further into the future, which was to say, we at IBM said, well, okay, we think superconducting qubits will work. By this time, transmons had been started to be promulgated, and we knew that they could be coupled by resonator couplers, and said, well, let's start thinking about layout. So here was a layout that I conceived of, and was sort of revealed in this paper in 2009, that yes, there should be a sort of carpet that would realize what's needed for these surface codes, that 2D connectivity. This was even a little more ambitious in the sense that you would use couplers simultaneously for nearest neighbor coupling and second neighbor coupling and third neighbor coupling. And this was enough. IBM actually patented that. It turned out that's not the wise approach. That the wise approach is to have a physical coupler for every coupling that you want to have. So if you want to have a fourth neighbor coupling, you have a coupler that will couple a neighbor to a qubit to its fourth neighbor. So not these sort of clever carpeted couplers. But still, I would say that this, formed the basis of what we do today. And if you've been following IBM developments, you know that they now have enhancements on these, which indeed have longer range couplers that will realize LDCC codes. And that's why I had this picture in here that, even the Starling of 2029 and the Blue Jay of 2033 plus will be having these carpets of qubits, of superconducting qubits. And so these things that became, or that started out as theoretical doodles, are in the midst of being deployed big time, full scale, to achieve where we want to be with quantum computers. So I just have one more postscript. I'm really at the end, except to say the following, that these setups are massive, because they have a lot of qubits, but it's the massiveness actually comes, and we realized this in 2009, because there are lots and lots of control wires. In this cartoon on the left, you see there are a lot of yellow squares. And the yellow squares indicate a place where an outside signal has to come into the chip. So it says outside signals have to come in densely everywhere on the chip. And that is indeed a lot of the, well, I'll say hidden or semi-hidden complexity of these IBM models is the enormous amount of wiring to the control apparatus that's needed. Now, this is something we commented on already at least 15 years ago, that this would be a feature of any quantum computer. This was a cartoon of some kind of layout of a spin quantum computer, and you'd need a cable to every point on the chip almost. And so a possible future development, which has been in our minds for years, but really we barely made progress on, is to put all the control electronics right next to the qubit. And this requires a style of classical processors that we don't know how to make currently. But if it were possible, then we could really have a quantum computer where you only have one or two digital cables into the apparatus, and that would control the entire quantum computer. I think that's a dream for the far future. I say here the motto of that is give your quantum computer an IP address. At the moment, they don't have one. Okay, so that's my story, and so I've taken you from very long ago to dreams for the far future, but maybe it's also in the service of very much in the here and now, and that many of you are thinking about how to exploit these amazing quantum computers that are going to be coming online, that have already come online and will keep coming online as we go forward. So I finished my lecture there, and I'm happy to chat a bit.
Hey, thank you. It's really an amazing lecture. You can see the chat is very active, and they really love your lecture. And it's really amazing to see like sharing different kind of milestones and all the famous people and the amazing work in the progress. So I think maybe you can stop sharing the screen, and then we can take on the.
Good. Yeah. Let's see. How do I do that? Stop sharing. Yeah. Yes. Okay. Yeah.
So okay. So I think we can pick on Q&A panel.Maybe you can see, but I'll read them, and I can actually highlight them, so we can start from the top. So, what do you believe the current limiting factor is for quantum computing hardware? Do you think it's the qubit themselves, the measurement tools, the gates, the materials, or something else entirely?
Yeah, in some senses, all of the above, or all of them need some progress. I think under the category of measurement tools is, among the things that I focus on. I do think that this issue of the massive nature of the control hardware is a big issue, and there are many different opinions about how that can go. That I know some colleagues who say that IBM is overshooting. That these devices that take an entire large experimental hall will just not be the way to go ultimately. But that one has to prove that. One has to prove that you can go simpler somehow. I mean, I don't think it'll ever sit on a desktop. Okay, but let me focus again on this. I think the qubits have to get a little better, but they've gotten so much better. We've tracked progress over orders and orders of magnitude, and at the moment I only look for factors of 2 and 3 and things. They don't need to get massively better. Also,
I think I remember maybe it was the summer school that I was in 10 years ago. I saw like this. I think the Koreans time started like nanosecond of the super-9 qubit, and now we are down to millisecond, which is a 6 order of magnitude.
Yeah, so we don't have that much more that we need to go on that track. Also, materials, probably not. I think we have the whole material set that's suitable. There are, of course, troubles with calibration and with the drift of quantum computers. And so it would definitely be good to have improvement in that regard. I think the existing materials are, well, marginally good enough. Maybe one would say that. Okay, I think that's enough about that particular question.
We'll move on to the next one. Is about the Landauer principle. How's that related to loss of information when you measure a qubit and it collapses?
Well, it's a truth, of course. Landauer's principle has to do with, it's a thermodynamic principle that says that performing a measurement and then resetting the qubit generates irreducible amount of heat. And that is fundamentally very, interesting, but it does not dominate the heat load of the quantum computer, certainly. So I would say more that we just need to have, the whole grasp of the idea of projective measurement and resetting is central to quantum computers, or you might say that you really have to believe everything about quantum physics to proceed with the quantum computer. You should not believe that we sort of only partly know the answers. The physics is all well known. It's just a matter of applying it in the right way.
Yeah. Okay. But the physics all well known sounds like before the dawn of quantum mechanics. We feel like we're just calculating the decimal points.
Yeah.
So the next one is a very popular question you also put earlier about topological quantum computing. Mm-hmm. What do you have any opinions on Microsoft announcement?
Yeah, well, I think the announcements are premature, in my opinion, and I don't really understand the forces that have led them to advance so many claims without having very good backup for them. Because at the moment with Microsoft, there's a mismatch between the actual scientifically reported results and what they say is true in their experiments. And on the other hand, there are people who critique even the experiments they have out there in publications and saying that, well, the interpretation is not so clear still. So well, wait and see. But I mean, the Majorana qubit or the Enion qubit is one that Kitaev announced in the 1990s, and it was beautiful conceptually. It was revolutionary from a sort of mathematical physics point of view. But it's been very disappointing in the lab. So, in my view, one really should currently say there's still no Majorana qubit. And I mean, Microsoft would say the other way around. But, if you have a qubit, by definition, it means you can do many, many things with it, and they haven't done it yet.
Yeah. Yeah. Okay, I can say something because that was my PhD, also topological quantum computing. I was trying to do, but using different material system, not ROI, but two-dimensional material. It's very challenging to find a Majorana zero mode.
Yeah, very delicate system.
Yeah. Okay. We'll move on next one, which I think you touched upon. Which I think the answer is no, based on your opinion. How long do you think we will have a personal quantum computer? Just like our personal computer right now.
Yeah, 38 and a half years. I mean, of course, my answer is I have no idea, right? But it won't be soon, right? I personally am a believer in the next era of quantum computing or quantum information processing, which will be indeed much more communication-centric, but involves capabilities that we haven't progressed on much at all, which is the idea of, with high fidelity, transferring qubits probably photonically from one solid state device to another. And but if that's doable, and if it's doable at significant distance, then that opens up many, many new avenues. And then it could make the desktop quantum computer, conceivable. We always make the point that, we now have computers that fit in our pocket, but actually mostly the computer isn't in my pocket. It's at the data center. And its power is because of its communication capabilities, that it can be functioning together with the gigantic backbone of compute services. So all of that is all conceivable as well with quantum as well, but it's going to take a new era of development for that to be possible.
Mm-hmm. Yeah, I think probably for the foreseeable future will be more like cloud-based, like what we are having now. Okay, let's see. Maybe we can take a couple, and then I think we can close. Let's see. Despite the failure of spin qubit, as you mentioned, doesn't method spin squeezing useful for amplification of signals and coherence of signal and coherence time of the qubit?
Well, first of all, I would not I myself don't call spin qubits a failure. I think of them as just a slow comer. So they're still not completely out of the race. I think. I mean, they're compared with Majorana, I feel they're very, very much farther along and have ideas for solving the remaining problems. Now, you're mentioning spin squeezing. Um, that's indeed another subject. I don't think spin squeezing by itself forms the basis of a qubit for quantum computing, but I think it does form the basis of a qubit for quantum sensing. So, and you're mentioning things like amplification. So maybe there's some concepts out there that I don't know about, but I don't think of squeezing per se as the golden route um, to spin qubit processors.
Mhm. Okay, I think we can take one more and we can close. There was a lot of thing in the chat as well about this. Why do we need a quantum memory?
Okay. Well, I bet there are people in the audience who know way more about quantum algorithms than I do. Um, well, I would say we'll surely need quantum memory. We're in the era where we've merged quantum communication with quantum computing. Um, we're in this era of Starling and Blue Jay, the thing that will just be functioning inside one box, no quantum communication in and out. You can indeed argue that there's no specific role for quantum memory. You just have to hold your logical qubit long enough for it to do its job and do a gate with some other logical qubit, and then it's finished.
Mm-hmm. Mm-hmm. Okay. I saw one that was specific to you, but maybe you want to answer. There's someone want to ask whether there's a better program in the Zurich Center in quantum computing hardware.
You mean that they're doing a better work than IBM Watson?
No, like
Oh,
bachelor degree, so they want to like
opportunity
start.
program for bachelor degree level, like dual stadium for get quantum computer. Oh, at ULIS. Oh, I thought you said Zurich. Sorry. Yeah, bachelor degree level. Well, maybe. I'd say usually you need a master's or a PhD to really participate in the work that's going on at those in those groups.
Mm-hmm.
So get your degree first, I would say.
Yeah. Okay. That's great. I think yeah, thank you very much for the really awesome lectures. I think like people really learn a lot from this historical background and also showing like different kinds of like different hardware platform to help people to understand like different choices out there, and then they can now tell like which one like expert, for example, like the Microsoft announcement that people really want to understand and how it is. So thank you very much. And yeah, and we're really honored to have you here. And as I mentioned in the beginning, that for me personally, this is like a full circle that I attended a summer school that taught by you, and now I'm organizing a summer school for others. I hope that it will inspire many people to continue this career. And for the rest of summer school, there will be some other events later today. So please
Yeah.
tune in for the lab 2. And yeah, thank you very much.
Okay. Well, I'm convinced, a lot of young people on the in the session, and I'm convinced one of you will be, the breakthrough leader of the future.
Yes, I believe so too. Thank you.
Okay.
Thank you, everyone.
Okay.
Bye.
Very good.